Hi guys, I hope you had a great long weekend. As promised, I said I would do optimization today, so this is going to take us a few days. And what I decided to do is go over what optimization is, the process, and then do a classic example in this video, the simplest of all examples, and then do a bunch of little videos based on types of problem. So remember in related rates, you had the sliding ladder, right? And you had a whole bunch of problems with the sliding ladder. And you had, I don't know, two people driving in opposite directions. And so you did a bunch of problems with two people going in opposite directions. Well, this is sort of how it's going to work with optimization as well. All right, so what is optimization? It's the process of maximizing or minimizing some quantity. And we use this all the time, every day in our daily lives, even if we don't realize it. So it's a super important topic. And essentially, what you're doing is you're just finding absolute or global extrema. The problem is, it's not a problem, it's a little twist, is that before, when you found absolute or global extrema, you were given the function, you were given the interval, and you would take the derivative, set it equal to 0, find the critical numbers, use the critical numbers and the endpoints of the interval to plug back into the original function so you could determine whether you had where the maximum and the minimum were. In this case here, you have to develop the function yourself. So again, in the respect like with the related rates, if you think about the sliding ladder, you had to have some kind of geometric connection, right? The ladder and the wall and the floor formed a right triangle, and so you used, a squared plus b squared equals to c squared, and then you were able to take your derivative and solve for what you were looking for. Here, you're going to come up with the function almost the same way. You're going to be given a scenario. You're going to have to come up with the function or develop the function. The other thing you're going to have to do is determine the interval or the domain of this function that you develop. So for some reason, domain in students, I don't know what it is, but this is probably a little more tricky than coming up with the function, just based on experience of many years. Um, you must read very carefully. So you're going to have to read these problems, and then you're going to relate that quantity to be optimized to some, again, geometric formula. Why do we need it? Because if you are going to be a business owner, you're going to want to maximize your profit, right? You want to minimize your losses, maximize your profit. If you're a contractor, my neighbor is a contractor, he builds houses. Well, he builds houses and he contracts the work out, but anyway, he doesn't want to choose, I don't know, the roofer that's the most expensive. He wants to build a good quality house, but he doesn't want to pay top dollar for, say, the roofing on the house. So contractors tend to want to minimize costs. If you're a doctor, you don't want to give somebody the wrong dosage of a medication. If you give them too little, it's probably not going to help them. If you give them too much, and that's a bad thing. So, they probably, and the other thing is they probably want to minimize the dose of a certain medication because, when you're on medications long term, that's bad for you too, even though it's not hurting you while you're taking it. But in the long run or the long term, it could be detrimental to your health. So, we use it all the time, and it's really important. Okay, so I wrote down some steps that should be helpful. Again, I can't stress it enough. Read until you understand the problem. Identify the quantity you must find, that is the thing to be optimized, and relate it to some geometric formula that you know. Make a sketch. I can't stress it enough. I stressed it with related rates. I used to go crazy about the sketch. I'm going to go crazy again. It helps you to orient if you can make a little sketch real quick, label everything, and it just helps put things into perspective for you. Express the function that you find using one variable only, so like f of x, right? Determine the domain, and then use your prior knowledge of finding global extrema to help you solve for what it is you're looking for. So I'm just going to take these examples right out of the book because you have the book at home. This begins on page 276 of the best book. And anyway, let's get started with the first example, the easiest example. Let me put the book under here. Let me twist this a little more. Sorry about that. Gosh, I hate this backwards thing. Okay, so we're looking over here at example 1. Okay. Now, he's telling you you're going to find the maximum volume. Chances are you're going to figure that out for yourself in the problem. So an open top box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide and 21 inches long by cutting congruent squares from each corner and then bending up the sides. Find the size of the corner square that will produce an open top box with the largest possible volume. What are we trying to do? We're trying to maximize volume. We want the largest possible volume. Okay, so I made a box. I took a rectangular piece of paper. It's terrible, I know. It was a rectangle, and I cut congruent squares of length X out of the corners. And now my focus, there we go. I guess I was moving too fast for it. I cut congruent squares of length X out of the corners so that way I could fold up the sides and make a box. Now, I don't even know what size corners I cut out. It would have been nice to know, right? But this is a box that can hold some volume, maybe the volume of paper clips or whatever. Is the size I cut out going to give me the box of maximum volume? I don't know, because I just got the corners out. But the idea is if we cut some piece or some square X out of the corners, we can actually find the maximum or minimum volume that the box can hold. The other thing I want to bring to your attention is if this side is X and this is length X, then when you put them together, the height of your box is X. So let's see, this edge is also X. The reason I'm saying that is because sometimes kids just, I don't know, don't see that right away. And then when you tell them, they're like, oh, yeah, now I see. Okay, so the height of this box is going to be X. And you know, I did it also, this is, you can see it a little bit better. I opened up a little box top that I had, and I didn't cut the corners out. They were already cut because it was a box. And anyway, you know, I don't know what this is. I didn't measure it, but it's some X length, and we can close it up. So even though this is a square container now that can hold some volume, it doesn't matter. The idea is what geometrically can I connect this with? I'm looking for the maximum volume. And I'm looking for the maximum volume of a box. Hey, volume, length, width, height, right? Geometrically, that's the formula. Guess what? You just found your function. So let me move this over, get it out of the way, swing this back over here. All right, so they told us that we have a piece of cardboard that's 21 by 16 inches, 21 inches by 16 inches. And that's the best rectangle I can draw. Okay. And they want us to find the maximum volume. That's what I'm looking for. And I know that volume is equal to length times width times height. And I need volume, or I need my function to be in one variable. So I'm going to call it X, right? I'm going to call it X because it just makes sense. If I'm cutting squares out of each corner, right, of length X or side length X, then what happens is when this goes away, you know, I cut it out and I cut it out. Now this side becomes 21 minus 2x. And when I cut this one out, these two, this length becomes 16 minus 2x. So my volume formula is going to be 21 minus 2x times 16 minus 2x times the height, which is x. Now, that's not the best, right? Remember, I'm going to have to take a derivative and set it equal to 0 and solve for the critical numbers in a minute. So I'm probably going to want to expand this out a little bit. And we can do that. We would get, let's see, we would get 4x cubed minus 74x squared plus 336x. And I'm noticing that everything's divided by 2, so you can just pull a 2 out. What would that be? 33 37. Okay. So I have my function. First part's done. Second thing is I have to find the domain. So I'm going to draw another little picture here. If this is my rectangular piece of cardboard, and I decide I'm not cutting anything out, I'm not cutting squares out, what's the volume it can hold? 0, right? I can't even build a box. So, I can cut nothing out, and there's no box, no volume. Can't make a box, can't have a volume. The other thing is I could cut, and I always use the side that's convenient. So I'm going to use this side here. I could use this side if I want to, but you'll see why I'm choosing this side in a second. If I cut a square that was 8 by 8 out of here, well, this little bit is 8, and this little bit is 8, right? And I don't know, we'll say 8 by 8, kind of goes like this, right? Now I have to cut an 8 by 8 out of this side. And so these are all gone. And now I'm left with this little strip of paper. Am I going to be able to fold up the sides and make a box? No. The reason I chose 16 is because it's divisible by 2 nicely. I could figure out this is 8 and 8 right away, make 16. So if x equals to 16, I still get no box. Okay, now does that mean my interval is going to go from 0 to 16? No, my interval is going to go from 0 to 8. I mean, I could cut a 16 by 16 square out, but I wouldn't be able to cut 4 of them, right? This would be 16 by, 16 like this or something like that. So remember, we have to cut a corner, each an x by x corner on both sides, and or all 4 corners, and I can't do that if it's as big as a length of 16 by 16. So it kind of just doesn't make sense. So I have my function, I have my domain. Now all I have to do is take the derivative, set it equal to 0, and find the critical numbers. So let's take the derivative, v prime of x. Well, this is a constant multiple, right? So that's going to go away. So if I take the derivative of what's inside here, I'm going to have 6x squared minus 74 x plus 168, right? So again, I already, there's a 2 here, right? If I divide both sides by 2, this is what I'm left with. And I can factor this. So we can factor this to, let's see, we can factor this to 3x minus 28 times x minus 3 times 4. I'm cheating. I'm just using the book, so I didn't have to waste time factoring. And again, if I divide both sides by 4, that 4 is going to go away. So what I'm left with is x is 28 thirds and x is 3. Now this one I can discard because 28 divided by 3 is bigger than 8. It's outside of my interval, so I don't need it. I only need what's in between and my endpoints. So this is the only critical number. What is the rule, or what do we do with absolute or global extrema? We take our critical number and our endpoints and we plug it back into the original function to see what produces the largest and smallest value. I don't really care about the smallest, I just need to find the largest because I'm looking to maximize the volume. So I'm interested in the largest output value from this. Well, remember that V was equal to 2 times 2x cubed minus 37x squared plus 168x, right? And if I plug in a 0, V of 0 is 0, no volume. If I plug in the 3, well, that's going to be 450. And if I plug in the 8, I'm going to get another 0. So you might already be asking yourself, is it usually the critical number that yields the max or the min or the value that you're looking for? Generally, yes, but not always. So make sure you test all of them. Okay, don't take any chances. A point is a point. So, what I know is that the maximum volume of this box is going to be achieved by cutting a square, a 3-inch square, out of each corner of my cardboard, and that's going to give me the box with the largest volume. Okay, so remember, I'm going to make a little series of videos, but I want to show you one other thing. If I put that function into the calculator, the original function. So if you're allowed to use a calculator, that's great. You still have to develop the function. You notice I put the function we found in the calculator, hit the graph key, and I could do the second calc maximum, right? A little to the left, press enter, a little to the right, press enter one more time. And bingo, when x is 3, y is 450. So, you could get a calculator problem, and that's fine. Sorry, I just need a little sip of something. That's fine, but just remember that in this case here, you're actually going to have to come up with that function by yourself. Again, we were looking to maximize volume of a box, so it just made sense that we used the geometric formula, length times width times height. Okay, so keep your eye out because there'll be another video coming out very shortly.